All right, so we left off last time talking about a method for finding a fraction between two fractions when it's not an obvious one. And this is the example we did. We did 33 over 427 and 34 over 427. So you do that, you add the two top numbers together, two numerators together, add the two denominators together, and that value will give you a number that is between the two fractions. Now, aside from the method by which we did this, the question I am asking you is, why in the world do we know that there is a number and that there's any method to do this anyway? What in the world allows us to know that? Any thoughts? What I want you to think about is I want you to think about one of the models that we talked about last time, which is the number line model. Remember that one? Where I drew a number line out and I said we could find the number 3/4 on the number line. We kind of broke it apart into sections and all that kind of stuff. Well, if you think about that number line approach, let me first write down the reason and then describe what the reason is saying. So the reason is because the rational numbers are dense. Dense does not mean stupid, right? Dense means that they were, well, from a number line perspective, let me say it this way. That is, you can always find a point halfway between two values on a number line. Right, so you imagine and you can think about, one of the ways you can think about this is think about like a calculator. Many of you probably not owned, but we've seen graphing calculators used. And one of the abilities that you have on a graphing calculator, and you have this in your phones and stuff too, is the ability to zoom in on things, right? And so you can look really, 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 really up close and personal at certain spots in a graph in particular. Well, if I can do that, then what that does is it takes these two numbers that appear very close together and it magnifies them. And when you magnify them, you can see that there's space between them, right? Well, that's what's going on. There's always space between any two rational numbers. Now, that doesn't work for some of the other number systems. So consider natural numbers. Those are the numbers you first learn to count. 1, 2, 3, 4, 5. There is no natural number between 1 and 2. Right? There are numbers, but there's not a natural number. So this feature is very specific to rational numbers. It doesn't work for every number system. All right, let's take a look at one of the things you haven't taken Math 1 before that you'll notice when we get into doing the group work today is that your book has several sections in it. At the end of a chapter, or at the end of a section, it has 3 sections of homework. That sounds really big. They just took the homework problem and divided it into 3 sections because they did. The first section, section A, and the second section, section B, are very similar. The difference is section A, the answers are in the back of your book. Okay. Section B looks an awful lot like section A, but I can assign those and know that you didn't have the back of the book's 8. You actually had to think through some of that yourself. Without that, extra help. And then section C has what I would call context problems. So they're problems either from a classroom, things that a student said and how you would respond to it, but from a teacher perspective. They're more geared towards application of these concepts if you were teaching them. And this is a problem like that. So this is a problem that would be a variety from that. In fact, it is from this section of material. A student simplifies the fraction m plus n over p plus n to m over p. How would you help the student? So the first thing you have to question yourself is, what did the student do? What did the student do? He may have subtracted, or he may have canceled it out, right? He sort of just removed the parts that they had in common. And that is a legitimate process, but not in this problem. That process is something you do, but you do it when there's multiplication involved, right? That you're able to do this canceling out sort of feature. But the student has done this with addition. So the kinds of response that I'm looking for in this problem, if you were given this problem too, is not because that's a property of multiplication and it's not a property of addition. That's a true statement. But you can say that all day to the student and they're still going to say, well, why not? Why am I not allowed to do that? Why doesn't it work? So your response needs to be very specific and think about what you would say to a child that would help them understand why it doesn't work. So I'm going to give you kind of an idea of how you could respond. It's certainly not the only response. But one way you could respond to this particular situation is to create an example. If I can create an example that shows it doesn't work, there's really not a lot of arguing we can do about it anymore, right? I mean, I showed you a place and with numbers, and it didn't work. So this can't work in general anyway. So take an example. So a numerical example might help. Now, the other thing that you'll notice in this particular section is the questions are not do the problem questions. They're asking you to explain something. So when you explain things, you should use language, right? Words. I don't just want a picture. I want you to say what you would say along with your picture, right? So here's a numerical example. Let me do the example first, and then I'll do the explanation that you might see or put along with it. So let me create some numbers. So let's try the numbers 3 over 5. And I want to rewrite 3 over 5 as 2 plus 3. I'm sorry, I said the wrong thing. 2 plus 1 over 2 plus 3. So this 3 over 5 is, and this right now so far, this actually works, right? This is the equation that's actually true. Does that make sense? Okay. So this is true. 3 over 5 does equal 2 plus 1 over 2 plus 3. So what the student wants to be able to say is true is that they want to be able to say that if I take 2 plus 1 over 2 plus 3, which looks an awful lot like m plus n over p plus n, that I should be able to do something like this. And they're not there anymore. And if I did that, what I would end up getting is the number 1/3. So if I use the student's method, I end up getting 1/3. But you can see from the original work I did that the number doesn't equal 1/3. It's actually equal to 3/5, and 1/3 and 3/5 are not the same value. And a very quick picture to show that they're not the same value could also be applied if the student weren't sure. You can create yourself a nice little box. All right, so here is a fraction bar or a rectangular picture, and I can show you that 3/5 of it looks like that. And if I take a diagram of the same size, okay, same rectangular bar, and I divide it into 3 pieces instead, then 1/3 looks like this. And very quickly and very easily, any child would tell you that the same amount's not shaped in, right? They don't match. 3/5 and 1/3 are not the same. All right, so this is sort of the example I would create, but just like in any classroom, as I'm sitting here talking at you right now, right? You're using language to describe this. You don't just give this child this example and move on to help somebody else. You actually describe what you're doing. So that's what you're going to do in your work. You're going to say something like, I create the above example, and you don't have to write out in words the example because you already did that, okay? So the above example, and show the value their process yields is 1/3, but the actual value of the fraction is 3/5. And 1/3 does not equal 3/5. Which I could also show using the above diagram or area model or rectangles or whatever. There's nothing special about what I wrote, but it's just an explanation of what I would say or what I would do with this example as I was talking about. Does that make sense? So that's kind of what you're going to see happen in this last section of the book where they have these problems. I'm calling them Part C problems. We'll see the end of that, but they call them connection problems. So you're trying to make a connection between mathematics and what you're doing with mathematics in the classroom. All right, we have one more problem that is interesting, and it also allows me to show you some cool stuff with the smart work, so I wanted to show you that. If we take a set of numbers equal to 1/3 and graph them on an xy axis, so that the numerator becomes the x coordinate and the denominator becomes the y coordinate, what type of graph would we get? Okay, so the first thing we've got to go up there to is where it says, take a set of numbers equivalent to 1/3. So I need some numbers equivalent to 1/3. And we did that last time. What's another fraction equivalent to 1/3? 2/6? That work? What else? 4/12, so let's keep it a little bit smaller just because my graph's going to get huge if I'm not. Can I go 3/9? Yes. Okay. And just so that I can show you that negatives work too, we could also have -1 over -3, right? Do the negatives on them. And -2 over -6, and so forth. And we could write this all day. I don't want to write them all day. We just need a few of them to show what's going to happen. Now what it says I'm supposed to do is I'm supposed to write these as ordered pairs. So in other words, this 1/3, I'm going to write it as the number 1, 3 as an ordered pair point. The numerator is the x coordinate and the denominator is the y coordinate. So everybody see the language and that's what it told you to do. Makes sense? So 2/6, what will this look like as an ordered pair? 2,6. How about 3/9? And now maybe you see why I want some negatives. What am I going to get? Awesome. So I've got 5 points that I can plot on an XY plane. So I want to show you where you can find it. I wrote this down because every time I do it, I have a difficult time finding it. So I want you guys to see where you go. If you take a look up here at these different buttons over here, one of these buttons looks like a landscape. That's a backdrop button. So I'm going to pick this over here. This gives you all sorts of insertable objects, pictures, diagrams, and there's really cool stuff in here. And there's probably more cool stuff for you than even is for me. But we're going to go underneath Gallery Essentials, assuming that I touched our button. There we go. And as you might suspect, we're going to look at mathematics. Right? And underneath mathematics, we're actually going to go into, this just happens to be where this is located, into statistics, and it's in pictures. And I have an axis in here. All right, so I'm going to choose this one. And now I have an XY axis. And I can make it larger if I need to, right? Just like you would in the computer in Word or something like that. You just drag around. This is great because I don't know about you, but I don't draw 3D very well. And so I've got a graph now on my screen that I didn't have to create, which is awesome. And I can plot these points that I have got listed as well. So the way I get this to go away as well, just because it's taking up a lot of my screen for projection purposes, I just click back to the notes right here. Zooming, there we go. And it makes it smaller. In fact, if I want to hide my slides over here too, which depending on what you're doing, you might want to, the way you do is you click this auto hide button. They say you do. And it goes away. So it looks much more like a PowerPoint slide if you do that. So I like to see it, so I'm going to keep mine there. All right, so I'm going to plot these points 1, 3. So some things to remember about the graphing. So this is your x-axis and this is your y-axis. So when I'm starting with the point 1, 3, I go 1 to the right along the x-axis and go up 3. And that's my first point, 1, 3. My second point was 2, 6, so I'll go 2 to the right and up 6. My second point was 3, 9, and you can see why I didn't want to do 4, 12. The picture doesn't go very big. Here's 3, 9. I've also got some negatives I was going to plot. I've got negative 1, negative 3, which is down here, and negative 2, negative 6, which is down here. And going back up, it says, plot them as points on the xy axis. So the numerator is the x coordinate and the denominator is the y coordinate. What type of graph would we get? So what do you think we might think we want to do with those dots? Connect them, right? Everybody wants to connect dots. I chose these specific numbers, but couldn't I have also chosen if I'd wanted to 1.5 on top? I could have. It'd be awkward. But I could put the number 1.5 on top and some other number on bottom. That's possible. Okay? So as I'm taking a look, this is what I'm making because I didn't unselect it. There we go. As I'm looking at this, I'm going to connect these because I really could have selected any of the x values between them. Almost. So I connected this, but I submit to you that there's an error in what I did. There is one point on this graph that I really don't have on the graph. Near 0. Because if I put 0 over 0, it is not equal to the number 1/3, right? Yeah, it's not. So I actually have a hole in the graph right here. There is not a point there. You just draw it with an empty hole. So the question is, though, again, right, this is a connections problem. This is a furthering what we're talking about problem. So I need to explain what I did, or I need to explain something, because the question asks, what kind of a graph do we get? Well, what is that graph? How would you describe it, generally speaking? It's a line, right? This is a line. So I get a line with a slope of what? What's that?
3 over 1.
Yeah, 3 over 1, or 3. So with a slope of 3, remember the way you find the slope of a line is you go rise over run. Rise 3, run 1. It's a slope of 3. And y-intercept at 0, 0, except that this graph has a hole at 0, 0. So it's very similar to a line, but this one actually isn't, because I've got sort of a gap in my graph.
So it only has a hole because you're looking at
Exactly. Any other point that I take, if I write it as a ratio, numerator, denominator, it will have the features of a line, and it will be on the point in the graph. Everything else is good. But 0 is a problem. Yeah, every other point would be fine.
But that's their term for that. So
There's not actually a hole. In fact, if you take a college algebra course or something like that, algebra, where you deal with line or curves that have asymptotes, sometimes you'll end up canceling out something in numerator and denominator. It will also create a hole in the graph, and it's just called a hole there too. Yeah, there's no more official name for that. All right, give me just a second.